My screen coming up good? I guess yes. All right. Let's see here. So this is session 4, which is the last official session of the Coding with Cody series. So the session 4 is going to be over integrating. Oops. Second, guys. Sure. So yeah. So this session will be about integrating multiple systems together, loops, and the final challenge. So integrating motors, multiple sensors, and decision-making logic. So essentially putting everything we've learned together to actually make the robot move autonomously, using conditional statements such as if, else, and switch to decide different robot behaviors, loop structures for automation, and then finally troubleshooting common Arduino programming issues. So a little introduction to decision making. Decision making, or the act of comparing items to change output, use two main systems. So there's if and else if statements. These are essentially just comparing two or more items with an if statement. Only has one outcome per statement. And there's something called a switch case. A switch defines many outputs based on one input variable. So I'll give an example here in a second. But the applications of these are like comparing values of sensors to see if they would fit into the threshold, take user input to make a user interface, and then really is used wherever two or more data sets need to be compared. So I'll go ahead and open up an example to show you guys code here. So here's a little introduction to if statements. So all this program does is it will take input from a button on the Arduino, and if it is pressed, it will change the state of the LED. So down here in the setup, we just have setting the LED pin mode, and also setting the button input, and then beginning serial. So in the loop, all we're doing is using an if statement to check if the pressed value equals 1. So if you see just a variable with no, like, for example, equal signs, it just means it's checking if it's 1 or true. So if pressed equals 1, it will then change the state. It'll then check if state equals 0, which that means is the LED currently off, and then it'll change it to 1, which is on. And then if the LED is currently on, turn it off. And then it will change pressed back to 0. And then if you notice, time since is equaling the time that it was changed. That is because down here in our conditional to check if the button is being pressed, we want to make sure that it doesn't continuously take input, because that time, if you do it that way, without the stimulus, it will just change that state a bunch of times per button press. Because Arduinos run at such fast speeds, one button press might seem very quick to us, but to the computer, it sees that like change a million times almost. So if the time is greater than 250 milliseconds, so if the button hasn't been pressed in the past 250 milliseconds, we'll set the press variable to 1 or true, and then print pressed. So I'll show you guys this in action. The camera will come here. Do that. So let me go back to the code here, upload it. So like always, for all of the actual robots, you'd use an Arduino Mega 2560. But for our test, I'm using an Arduino Nano. Then COM10. If we go ahead and upload that code, we'll first compile then upload. Compiled good. Didn't make any errors this time. Then let it upload. Perfect. Open the serial monitor. And now, every time I press the button, it turns on and off the LED. Also, another thing with this current logic setup. If you hold the button down, it just flashes it every 250 milliseconds. So essentially, the main thing I want you to take away from here is just how to use ifs and else if statements. So an if statement is simply just the statement if, followed by the parenthesis, and then the conditional check. So for example, top one here is just if the press value equals 1. Else if statements, they're very similar to if statements. It's just they only are triggered if the if statement above it is false. And then it will, this is false, it'll then trickle down to here and check this state. Back to our presentation here. So yeah, that's just a very simple application of if statements. Obviously, when you're using them in our robot, they'll be a little more complex. So loops. So there's three main types of loops. There are, first let me tell you what a loop is. So a loop is just a way of repeating the code over and over again. So if you noticed, in the main Arduino code there's a void setup and a void loop. The void loop just repeats indefinitely. So a loop is just a way of repeating code over and over again. So there's three main types of loops. There's a while loop, which is just it will continue to loop run the code inside of the loop while loop until the statement inside the parentheses is false. I'll go ahead and show you that now. While loop. So this actually has all the loops in it, but for right now, we just want to focus on this right here. So for while loop, it's just the statement while, and then the conditional to check if it that you want to check. So this is while I is less than 5, and if we go up to the beginning of our program, we set while I to equal 0. So it will check as long as I is less than 5, it will run the code in here. So this code just simply prints out while loop and then the value of I, and then a new line. A lot of times in previous demonstrations, I've used something called print ln, which is just print with a new line before it. Another way of doing that is just very simply writing in a print just backslash and n. This is just the syntax for a character turn outside of the using ln. And then here we have I++. So in while loops, you have to, the while loop doesn't automatically increment this value. So you'll have to actually increment it in the code. I++ it does the exact same thing as I equals I plus 1. So it just increments it 1. And then we're just waiting a second so we can actually see it work. I'll demonstrate all of these here in a minute. Let's go back to this. So the next type of loop is a for loop. So this loops until a condition is met, like a while loop. So example, I is greater than 3. But the difference is it also will increment every loop. So it doesn't have to require the I++. So show you guys that. So down here is a for loop. So the syntax for a for loop is just for, followed by your variable that you have to create for checking. So this example, we're just using j. So integer j started out with 0. And then here is the value that we're checking for each loop. So this is saying as long as j is less than 5, continue looping. And then at the beginning of each loop, it will increment j by 1. So for this one, we're just, same thing as above, we're just printing out what j equals and then delaying for 1,000 milliseconds. But the main difference between a for and a while loop is a while loop, you have to increment the I automatically, whereas for a for loop, we have to increment an I manually. And while for a for loop, it will automatically increment it for you. This has its advantages for stuff like this, but in a lot of more advanced situations, a while loop can be a little more powerful because it has just more customization, I'd say. Sure, let's bring it back again. So there's one more kind of type of loop, something called a do-while loop. So a do-while loop will run the code once before it even checks the while statement. So this, for example, you put it will run the code once. So say your robot goes forward, and then after the code does once, it will then check what's in the while statement to see if it wants to run it again and again. So just show you that. So do while. So start out with you do a do, and then you do brackets, and you don't have your while statement until the end. So the way this works is it'll do this first. So it'll come to the do, and then it'll run all the code in here. And like before, we're just have a simple variable I incrementing it. And then after that code has ran once, it will then check the conditional statement. So while I is less than 5. So since it will be less than 5, it'll then repeat this for an extra 4 times. Like always, we have to actually manually increment it. So I'll just show you what this does. This isn't actually really using any of the Arduino's I/O or anything. We're just using it as a little processor essentially. Do that. Open up the serial monitor. So you notice for the while loop, it will increment it 4 times, and then the for loop does it 4 more times, or 5 more times, and then the do while. I'll stop it there so I can actually explain a few things. So you also notice that for none of these actually ever reach 5. So if you look in our code, we want it while I is less than 5. So because it always increments after it runs the code, or after it runs the print statements, it'll then say I is equal to 5, and it'll come up here and not actually run and show you the 5. Let's see here. And then the for and the while do while loop the same way. You can, if you want to actually display the 5, you can just do very simply while I is either equal to or less than 5. I'll just show you that really quick. Cool. What else? I'll plug my Arduino back in. Oh, we have an issue. Oh, yep. Make sure it is the equal signs after the additional checking. So, load the code. There we go. Open up the serial monitor again. So here's the while loop going, and then this time it'll actually output the 5 because I equaling 5 is actually still true in this statement. I think I'll just change that. Okay, we'll go back to this now. So yep, that. So use cases for loops. So loops are essentially used wherever you want code to run many times. So for example, if you wanted a robot to drive forward until it saw an object, you could use a while loop. So for example, while this sensor reading was less than a certain value, continue driving forward. They're also good if you want to do a bunch of movement over and over again. So say, for example, you want to make a square with a robot. Instead of having to write out all of those go forwards and turn lefts, you could just simply put it into a for loop that runs 4 times. Just drive forward, turn left, and do that 4 times. And it'll save you from having to manually write out all that code. So integration. So integrating looped conditional statements and functions will allow for more complex movement in this task design for robots. So one way you might use this in the game is say you have to go pick up an object. That would take a lot of conditional statements, obviously, but you could say have a sensor on this front of the robot and position yourself based off of a prop. And if you saw that, you know how far away you were from like that. So, and then here, yeah, I need to show you guys that. So I'll actually, for the autonomous one, I'll write it with you guys so you can see that. Let me share my screen again. So we just have a blank Arduino tab here, and we want this to say run into a square. So because we're using our ESCs to be servo values, you have to always include servo.h, and then just assign all of our servo classes for the motor controllers. Perfect. Down here in setup, we have to go ahead and attach our servo classes. So attach it to a pin. I'm getting all of these pin assignments just from the forgiven code that uses controller inputs. That's another good thing. Looking back at your previous code for references is always a good idea. So that way you don't have to go look at your Arduino or your wiring diagram to actually figure out what pin everything is on. Perfect. That one is make some comments so we know which motor is which. Perfect. So in the loop, we want it to drive forward and turn. So to begin with, we'll set up a few functions just so we don't have to write out all of the servo write commands over and over again. So let's drive forward. And then just going to copy and paste this from the previous code so we don't have to write this out a bunch of times. So here we go. Spacing correct. Doesn't actually matter that much. And again, you should notice motor 1 and 2 are different than 3 and 4. This is just because one of them on the left side of the robot and one is on the right side. So when you're looking at the robot, the motors are spinning in opposite directions to go forward. For now, we'll just make that do that, and we'll have a second function stop the motors. And again, we'll just copy and paste our previous code. Yes, a little bit of effort. And like always, 1500 is stopped. Then we'll have a turn left function. So we can complete our story when we drive in. So another thing is we don't have actual positioning data from our motors. So don't actually know if this will be a perfect circle without testing it, because we're just going to be turning for a certain amount of time. Here, a lot easier as copy and paste this. Then just write that as all of these for 1600. We'll spin them all in the same direction, but since 2 of them are reversed in the other one, it will make it turn left. And this one we will put a delay. We'll just turn left for 1 second. That probably isn't enough time to actually, like that, actually, that might be enough time to actually fully turn right. That's something you kind of have to do a little bit of testing with. And yet again, don't write everything, just copy and paste. And we want to just stop the robot. Another fun key binding that's very handy is if you want to change a bunch of lines of code at one time, Control-Alt will allow you to have multiple cursors on different lines. So if you need to change a bunch of values really quickly, that's very handy. That's it, perfect. And a nice little practice I always like to do is just write a few comments above each function so you know what it does. So this will robot for 4 seconds. This one will stop all motors. And this one will drive forward till stop function is called. Another quick change we could do. Instead of having to write out this, we could just call the stop function and it'll do the exact same thing. That's another thing I forgot to mention last week. You can call functions inside of other functions. So it's a nice little way of making your code even more easy to read. All right. So since we want to drive in square, like a for loop with our incrementer starting at 0, we'll make that incrementer go till I is while I is less than 4. That'll increment it. That'll do the loop 4 times. And another thing. All right. Another thing is for a for loop, you have to have a semicolon after the first two statements. So for the initialization of your variable, and then for your conditional statement, you have to have a semicolon after it. But for the final incrementer, you do not. So what we'll do is we will drive forward. And instead of using delays, we're going to use a millis statement just so we can. So we'll have a double here. Actually, we need to make that right. Double of time start. Like that. So drive forward. Then we'll make our time start equal to millis. And now what we'll do is, this is another good use for a while statement. So while millis. So we'll use if statement here. If statement will make a little more sense. So if millis is greater than or equal to time start plus, we'll just say we'll go forward for 1,000 seconds or 1,000 milliseconds, sorry. Then we will call the stop function. So the reason you want to make this a millis instead of delay is, for example, if you had a bunch of background processes going where you wanted to check a bunch of sensor data, this would actually allow it to continue happening. If it was a delay, it would stop. The processor would do nothing during that delay timing, which is an inefficient way of using your hardware. Just allows a little more flexibility. And then we will actually put a delay here since we have nothing else going on. We'll wait 2 seconds and then we'll turn right. Or turn left, sorry. Make sure that was the right call. Yep. So some test space here. So what this code will do is it will drive forward and then it will wait for 1,000 milliseconds, or 1 second, and then it'll stop the motors and it'll delay for 2 seconds and then it'll turn left. And it'll keep doing this, it'll do this 4 times, which will make a square. So just for examples, I don't have a robot that I can show you this on, but I will show you all that working with serial. So we'll go here to setup. Serial begun 600. Another thing, you can change the baud rate. It doesn't always have to be 9600. So that's just a very slow setting that won't cause too many other errors with like processing speeds. But if you need to get more data quickly, you can have that up a little bit. So just print ln, and we'll just say like going forward. So we can see what's going on. And then we'll also put one down here with the stop. Then we'll also put one around here with a turn left. Perfect. So now we'll give this verify, make sure it actually compiles. Oh, we've got errors. So let's see here. Ha. So if you notice right here, we got a semicolon. That was causing that to be undefined. So always make sure you have all semicolons. That is a very common mistake, and you will more than likely make it a few times. I know I shall still do. All right. Uploading. Done uploading. Go into the serial monitor. Here, we'll actually restart this so we can actually start from the beginning. So we're going forward, turning left, then going forward, and turning left. It'll do it a bunch of times. I just wanted to show you guys. Oh, another thing we noticed, we're never actually calling stop. So we'll go ahead and figure out why that is. So if millis greater than or equal to time start plus 1000, see here. Oh, yep. Now I know why I'm making a while statement. If we make this a while statement, it will actually work. But since we have it as an if statement, it's checking it once, and then it's ignoring it, and it's going down here and doing this. So the way if statements work is if they don't run this code inside of it, it won't stop and wait for it to actually run. So it was just checking this, realizing that hasn't happened yet, and then it's going down here and turning left. But because we set time start to millis every loop, this never actually got entered. So what we can do, this is a good use case for a while loop. At this time, the while loops have to be true to actually work. So while it's lower than that, we just want it to sit here and do nothing. And then after that, so this right here will essentially stop the code until this is being called, which is just essentially another way of having a delay at this point. But I'll still show you this working. Let that code just so we can see it work. Forward, stop, turn left. So yeah, now it's actually doing that. This is actually a pretty bad way of implementing this. A better way would just be using a delay to actually get it to work with millis and have it non-blocking. You'd also have to put an if statement down here. Actually, another good way you could do this is just put that right in there. And do make sure we'll have to get that while loop there or it won't work. It has to actually wait for that to occur. Put that code. Going forward, stop. Turn left. Perfect. Yep. So that's just how you'd make a very simple square. Now, that's not going to get you much. So another addition to this is we could have, say, a different program. This time, I'm going to get rid of that for now. It's having the robot drive forward until it detects a wall, for example. So to do that, we obviously need our sensors. We'll include our library for our ultrasonic sensor. Like example, make sure I have the right one. So yep. Just copy and paste this in from a then we'll initialize our sensors, and then in the loop, I have a while loop, and for example, while the distance, let me make sure I'm typing that right. Yep, distance sensor, oh, dot, yep, measure, measure distance. Yeah, measure distance, centimeters. cm is, we'll just say greater than 25. So as long as it's farther than 25 centimeters away from a wall, we will drive forward. Or is it go forward? It's drive forward. And then if it, for example, cannot drive forward, we'll have it stop. And then we'll just have it turn left. So what this would do is it will actually, I'll actually show this working. So I will tell in the this data right here, just so we can actually see that. Verify the sketch. Actually, oh, what's our issue now? Okay. Yeah, verify that I typed that right. I didn't type that right. So that should have been a lowercase m. Small things like that will sometimes get you. That should compile now, hopefully. Yep, perfect. So let me go ahead and change back over to my other camera. Perfect. So what we need to do now, we look at our thing. We need a ultrasonic distance sensor on pins 13 and 12. So I'm actually going to unplug the Arduino and just take the lightning button off, just so it doesn't get in our way. So we'll grab our ultrasonic distance sensor here. Perfect. So look here, we have a ground. So we'll plug that into the ground of the Arduino. Then VCC, so in this instance that'll be 5 volts. 5-volt one there. And then trigger and echo. So I think trigger is pin 13. 13 is that right here. And then our echo pin is pin 12. Now we'll plug that in. Need to re-upload this code first of all. Put all of our serial monitor and all that good. Point this just towards the ceiling for now. Perfect, done uploading. Hey, it works. So right now we're going forward because the distance is less than that. But if we change this to say, see that, and now it is stopping and then driving, turning left. So anytime that this data less than 25, so we're at 24.8, and then it turned over. This is not precisely reading here. Maybe point at something I can actually maybe here. Let's change that value so I can actually show it a little better. Change it to 5 centimeters. Right now I don't have enough space to show that properly. File the sketch. Uploading. There we go. So pointing at the ceiling, pointing that way. Then 15, still going, 10, 11, then it reached -1. So that honestly seems more like an error than actually data. So let's try that again. 10, 9, was 5.4, and then it reached below 5, and then ran the stop and forward. So this is just a very basic implementation of a while loop for distance sensing. But for example, if you need to in the game drive through a gate, you could have one like an array of these sensors, and that would show you if you need to turn left or right to actively get through that gate. Because we have pretty good distance in our distance guide, but sometimes they change just a little bit. So it's nice to have a little bit of active feedback in the system. So, second, go pull up. What I need to pull up. So, another thing I need to touch on here, pull up my code again, is documentation and comments. So, in code, it's always a great idea at the beginning of each program is just to make a little comment block with who wrote it, when it was wrote, and what it does. So in C++, if you don't have to type out the / for each comment, you can just have a slash and then a asterisk. And everything inside of that is code, is comments. So for example, this code it's just a autonomous, let's say autonomous until reaches a wall. So purpose, it's just very simply drive forward till a wall is found, and then name of who wrote it. So my name for now, and then date. So the main purpose of this is when you're later on, say you're working on your documentation for your scoring, it's always nice to have like a timeline. So having a date is always a good idea. So for example, you can say like have like a timeline of all your development. This way you actually know when that was. Also, it's good to know who wrote it. So that way, when you have questions about it, you know who to go ask. And then another thing is always just have comments saying what each line does, for example, including sensor library. And then above each function, I always like to have a little comment block. If the function actually has parameters, so for example, time or something, I always also like to say what the parameters are. So int time is equal to the time for delay. Right? And then just say like that time. But it's always good practice to have so when someone looks at your code, they know what it does. And more importantly, when you look at your code in a few months' time, you can go back and understand what it does. But let me pull up the presentation again, wherever that went. There it is. Oh, one second. That's not perfect. Why are you sharing it now? Well, so there's a few common programming errors that you might run into. So, for example, if your code doesn't actually compile, I'll show what that looks like again. I'm gonna go back to here again. All over the place today. Say you mistype something and make it lowercase, and then when you try to verify it, spelling sketch, you'll get all this red text. So to understand what this does, it'll say, first of all, in which function the error is. So in this case, in the loop, too few arguments to function turn left. Oh yeah, so that's actually an error that I made before realizing this. So if you notice here, turn left, it won't the time. So make sure you actually fit time. So notice here in the void stop function, class servo, which is stating that your servo class, when you assign your motors, has no member written right microseconds. So if you look down here, a member is just what goes after the dot. So it'll say that's not valid, but sometimes afterwards it'll say, did you mean write capital microseconds? That's why it's always a good idea to look at what they're actually saying in these errors, because they're very descriptive of what the actual issue is. And sometimes it'll also show you things that aren't actually too important. This is just saying I have two libraries that have the same name, but that won't actually stop the code from running. Perfect. Back. Change window. So another thing is if a conditional logic or loop is not being triggered. So that's, for example, if you write a if statement for if a certain value is reached, do something, and if you're never actually getting into that when you expect you should be, it's always good to make sure you have your less than or equal to or greater than equal to actually the right way around. So, for example, if you want something to be after the current time is greater than 1,000 seconds plus the previous time you had captured, you always want to make sure you actually have that as greater than and not less than. If you also notice that, say, 3 of your motors are spinning, but one of them isn't, and you just change the code, go back and double check that first. In the code, you have all of your pin assignments correct, and then actually check on your Arduinos to make sure it's plugged into the assignment that it should be. And then if all else fails and you can't fix the error, try commenting out different sections of your code to see if it's actually causing the error, but it's not being shown. So sometimes when you're writing more complex code, it'll give an error that just doesn't make any sense. So I always like to compile as I'm going. So say write one function and then compile to make sure that function isn't going to give you errors. But if that isn't working, try commenting out sections of the code that you're not currently using or aren't related to the issue, just to make sure you're not having interlacing issues. And that is all I have for this session, and this is the last session. I just a little homework assignment. Go try to set up an obstacle course. Get a few sensors and try to see if you can make the robot actually autonomously drive now. So that's all I have. Does anyone have any questions? No questions?
Cody, it sounds like you got a lively bunch there. You guys need to settle down just a little bit, huh?
Yep.
Hey, did you share the RDL Ohm's Law printed circuit board with them?
I did not.
That'd be cool to show them. A new addition to our RDL store.
Let's see here.
Yeah, Cody's been working on a secret mission project, how to teach kids Ohm's Law. Yep. And so he'll bring it up and show it to you. These are for sale in the RDL store. It's one of the individual student activities. I think most of you have soldering irons or soldering stations, but it's always cool to send the kids home with a trophy, if you will. And so one of the first things that we like to teach kids, other than coding a robot or doing some CAD and Onshape, is to also do some soldering and learn some basic soldering skills with the printed circuit board. So Cody, I think he's going to bring up some pictures.
Yeah, I'm bringing up a 3D model of it. It's just my computer's taking a second here.
Cool. And Cody, thank you very much. I think the feedback for this 4-week session, these 4 different sessions, has been really positive, and we really appreciate your hard work and getting these guys going in some basic coding with their advanced terrestrial robots. That's going to be really good. And don't worry, you guys will see Cody again. Hopefully, I think November 15th in Murfreesboro. And then I think we're going to fly him up to Boston, Massachusetts in December. So if you guys are competing in Boston, you'll see him again.
Yeah, 1 second, guys. I'm trying to pull it up. It's just.
Hey, Cody, this is Sergeant Ruben. Can you hear me?
Yeah.
Finally, I can hear. I do have a question regarding the code that we received. Have we made a headway on the little glitch that we had before?
Um, with the like jittering, I'm guessing.
Yeah, yeah.
So not yet. We're still working on that. It's actually also, if you want to get a little more in depth, it's also a great way of trying yourself your hand with more advanced things. But yeah, we're still working on that. Hopefully we'll have that here soon. But
Okay. Thank you.
mhm. So, finally, here's a quick picture of the Ohm's Law PCB.
So it comes with resistors, LEDs. Also has a what do you call that? The switch,
Yeah, so it's a dip switch. It's not actually
dip
shown here in a
switch,
3D model, but yeah.
right? Dip switch, and so you can change the resistant values. You can put a multimeter on there, and you can actually see the drops for voltage as they cross over to the different resistors. And I think we're looking at including some lab sheets to go with these um, circuit boards, to where the kids can figure out in math and just basic algebra, the voltage equals amperage times resistance. Then how you can figure out if you don't have one of those values. So kind of a cool little exercise. We're super excited about it, and Cody did a really good job with that. And like I said, the kids get to take it home. I mean, it's $12, and so it's not a bad investment. And you could turn it into a 2-day exercise, or you can do it in 1 day. But I think if you added the Ohm's Law labs, you could build up to it too, to where you have maybe a Thursday, Friday soldering, and then they get to take that home for the weekend and show off all their family and friends. It comes with a battery holder too. So I think are you putting double A's or 9-volt battery into it? Which one are you using?
Yeah, it's 3 AA's.
Yeah, so some double A batteries. Um, and of course, the LEDs light up and they can change the configuration. And for a kid that's never soldered or never made a LED come on, it's going to be a game changer. So we've used these in the past at all of our STEM camps, and then of course during our initial robotic season, it's always a good opener.
All right.
Hopefully everyone's doing well out there. You guys enjoying the season so far?
Dennis, we're good so far. When can we when is the last day to register for the Boston? Because I don't think there's a deadline for that one.
The deadline to register for all regionals is October 15th. But don't worry, because of the Army JROTC program, we have you guys penciled in, so you're good to go. I think, have you been getting emails from us?
Uh, as far as like, yes, like the competitions and all that. Yes, I just wanted to
Yes.
make sure.
And let me
Thank
mention,
you.
we have a coaches meeting tomorrow at 4 o'clock. It
Yeah.
will be recorded in case you cannot make it, but I would highly recommend, if you could. You're going to hear from some of the best. A lot of our coaches that have been with us for the whole 8 years we've been doing this, they'll be online, and they can tell you some of the best practices of a RDO coach. We'll have some newer coaches, that have been there for 2 years, 3 years, and they can tell you, they'll share some of their frustrations with you and how they overcame some of that. But again, it's a big community, and so we just want to be able to share some of that communication with you, and we try our very best to get everyone in within an hour. But like I said, will be recorded. I know our friends over in Germany, you guys are like lighting candles to stay up all night, right? So that you can be with
I'm drinking my 15th cup of coffee today.
us. Oh man, three cups, and my doctor said no more unless you want to increase your blood pressure medicine.
Yeah,
But
I haven't blinked in 4 days.
Wow, I know. I remember those days on the airplane in the Navy. The coffee tasted like tar. Um, but but thank you guys very much for giving Cody your attention. Hopefully, you've learned a lot. And don't worry, Cody's not going anywhere. He's going to be with us for quite some time. So if you need anything, feel free to reach out. We're here to help.
Thank you.
You're welcome.
Okay, thanks, guys.
Thank you. Bye bye.
Thanks, Dennis. Appreciate it.
Hey, Christian, how are you, man?
Doing good. Thanks. Hey, I heard a couple of questions from our guys. Just let them know. I mean, we're making this December. We're gonna pay for it, and we're gonna invite
Yep.
those groups that we discussed. So
Yep.
everyone should know the 9 teams are paid for it already. Hopefully, the contract is good to go in the next 30 days, and we'll execute.
Yep. All right. That's good news. So yeah, we're excited. Boston. Yeah, Boston's going to be a lot of fun. We're I think for the majority of our staff, we're bringing everyone in. Generally, the staff will drive from Tennessee to either Georgia, Virginia, or Tennessee, the one in Murfreesboro. But for Boston, we determined that it's probably better for everybody to fly in on that Friday, and then we'll probably fly them out on Sunday. But we want to make sure that the event in Boston is supported. We really appreciate the partnership with JROTC and getting you guys launched. I mean, from that first cohort of 3 with Gonzalez and Rodriguez and Bowker, and then the follow-on cohort, you guys have worked really, really hard. And we know that you're passing that on to your kids. And so the students are working hard from what I hear from some of our coaches, our JROTC coaches. The kids are super excited. And that's what gets us pumped about all of this is that learning, that student learning that we know is taking place in the classrooms because I can hear it in the new coach's voice. So, God bless everybody. We appreciate you and thank you so much. We'll be in touch and you know how to get a hold of us if you need us. Okay.
Thank you so much for everyone. Thank you.
You're welcome. Thank you.